A small, unmanned boat approaches a beach held by Russian forces. Its ramp drops. A tracked ground robot rolls onto the sand and opens fire, while an aerial drone watches. No Ukrainian soldier appears on the shoreline. The footage was released by Ukraine's 123rd Territorial Defense Brigade in July 2026. The brigade described it as the first known combat mission in which an unmanned maritime platform carried and deployed an armed ground robot onto enemy-held territory. The location was the Kinburn Spit, a narrow strip of Russian-occupied land at the mouth of the Dnipro-Bug estuary. The video proves the deployment and firing. It does not independently prove what the robot hit, whether it survived or whether it returned. This was closer to a field experiment than a new D-Day. But it tested a serious question. Can machines enter the most exposed part of an amphibious operation before people do? An amphibious landing forces an attacker to cross several hostile environments in sequence. Troops must travel over water, leave the protection of their boats, cross open sand or mud, and then move inland before the defender concentrates fire. During those first minutes, the attacking force has almost every disadvantage. Vehicles can bog down. Landing craft can be struck before unloading. Radios may lose contact between units on the water and units ashore. Heavy weapons, air defense, medical support, and ammunition are still arriving. Until the attackers create a secure beachhead, the sea is behind them and the defender is in front. Normandy succeeded in 1944 through deception, overwhelming support, engineering, and immense logistics. Even then, several beaches became killing grounds. At Inchon in September 1950, United Nations forces accepted extreme tides and narrow channels because those obstacles made the landing unexpected. Surprise produced an operational breakthrough. Gallipoli showed the opposite. Allied troops landed on the Ottoman coast in 1915 but could not break out. Defenders held the high ground, the campaign stalled, and the attackers eventually withdrew. The lesson is not that every landing needs another Normandy. It is that the shoreline compresses risk. A small failure in navigation, timing, fire support, or logistics can trap people in the worst possible place. Modern surveillance makes that problem harder. Drones, thermal cameras, and radar can watch a coastline. Mines can block the approach. Artillery and FPV drones can attack boats or vehicles while they are still exposed. Electronic warfare adds another layer. The attacker needs radio links for navigation, aerial observation, and command. The defender can jam those links, imitate signals, or search for the operators transmitting them. Early in the full-scale invasion, Russia gathered amphibious ships in the Black Sea and threatened a landing near Odessa. That assault never happened. Coastal missiles, mines, surveillance, and prepared forces made the approach increasingly costly. So the modern landing problem is not simply reaching the beach. It is reaching a beach that may already be measured, mapped, and watched around the clock. Ukraine has spent years building systems for that environment. Its sea drones began as explosive boats used against Russian warships and naval infrastructure. Later versions added larger payloads, sensors, and weapons. They led a country with a badly reduced conventional Navy contest, parts of the Black Sea. Ground robots followed a similar path. Ukraine's defense ministry says they now support logistics, engineering, reconnaissance, evacuation, and combat. The ministry reported more than 50,000 missions during the first half of 2026. A robot carrying ammunition or a wounded soldier can remove several people from a route watched by drones. The Kinburn operation connected those separate developments. The maritime platform became a carrier. The ground robot became the payload. An aerial drone provided another view of the landing. Human operators remained in the system, but they did not have to stand on the beach beside the machine. That sequence matters more than the individual robot. A maritime drone could deliver a reconnaissance vehicle, a decoy, a communications relay, a mine-clearing tool, or a small supply carrier. The first machine ashore could search for obstacles or provoke a defensive response. If the defender fires, an aerial drone may reveal the position. If the defender stays hidden, the robot may move farther inland. The defender now has to decide whether a small contact is a disposable probe, the beginning of a larger raid, or a distraction from another landing point. That sounds powerful, but the limitations are severe. Saltwater, sand, mud, vegetation, and steep banks can stop a small tracked vehicle. A carrier that beaches at the wrong angle may not lower its ramp. Batteries limit range. Every kilogram of armor or ammunition reduces mobility and endurance. The communications problem may be harder than the mechanical one. A remotely operated weapon needs a dependable path between the robot and its human controller. Terrain can block that path. Jamming can degrade it. A relay drone can extend it, but that adds another machine that must survive and another signal the defender can attack. An armed ground robot also cannot create a beachhead by itself. It cannot hold prisoners, treat casualties, repair every damaged system, or carry the air defense and logistics needed for a sustained force. If the robot is disabled beyond the shoreline, recovery may expose the very people it was supposed to protect. Scale creates another burden. 10 robots need more carriers, radio channels, operators, spare parts, and batteries. 100 robots are not one robot multiplied by 100. They become a command and logistics problem. This is why the Kinburn footage should not be treated as proof that robotic armies are ready to replace Marines. It is evidence that one dangerous step can be separated from the soldier who would normally take it. The most realistic future is a mixed force. Machines scout routes, carry supplies, draw fire, clear obstacles, and enter contaminated or heavily observed areas. People make decisions, adapt to unexpected conditions, hold ground, and manage the consequences. For Ukraine, that trade is especially important. In a long war, trained personnel are harder to replace than vehicles. A destroyed robot is still expensive, and a failed mission can reveal tactics to the enemy. But losing a machine is not the same as losing the people who would have crossed that beach. The Kinburn landing may remain a niche experiment. It may also become the first visible example of a wider method in rivers, estuaries, islands, and exposed coastal positions. Its importance will depend on whether Ukraine can repeat the mission under jamming, bad weather, prepared defenses, and real logistical pressure. The most dangerous distance in an amphibious assault has always been the gap between the water and cover. Ukraine's experiment asks whether some of that distance can be crossed by metal first.